My name is Paco, and just if you're joining us, this is Anyscale Academy. We're talking about Ray using reinforcement learning. My name is Paco Nathan, and we'll be covering material that's in the rllib_tutorials repo. In particular, we'll be working with how to set up a custom gym environment that works with rllib. We'll be looking at multi-arm bandits, some aspects of bandits, and then we'll be looking at a recommender system based on reinforcement learning, something that's using the gesture data set for joke recommendations. A lot of this will be about compare and contrast with like what types of approaches are suited for particular use cases. Again, this is running from 10 a.m. Pacific to 11:30 a.m. Pacific, so hour and a half. We'll structure it in terms of a little bit of introduction, some lecture, cover just recap from the previous session, which was intro to reinforcement learning. So there's a couple of key concepts there we want to cover again, and then we'll take a look at, for instance, multi-arm bandits. What are some of the trade-offs for different types there? How are those indicated for particular use cases? And then from there, shift into reinforcement learning for recommender systems. What's some of the thinking that goes into building a recommender system? Yeah, okay, it's 10:06. I think we'll call it good. We've got, wow, a lot of people in. Well, welcome. Like I said, my name is Paco, and I'll be leading this here. Please feel free to ask questions at any point. There's the raise hand, there's Q&A, there's also the chat. Sophia and I will be looking at the chat. A lot of times when I'm doing screen share, I probably won't see the chat quite as immediately, but I'll stop and check out. So please feel free to ask questions at any point. I'd like to get into that kind of dialogue. All the materials are online on GitHub. We'll be working with Jupyter notebooks that encapsulate all of what we're going to show. And there are instructions. Let's go ahead and shift over to screen share. Great. Okay. So there's a GitHub repo, Derwent AI, rllib tutorials, and on here you've got all the materials for what we'll be working with today. In particular, to get started, just clone the repo and connect in the directory. You can do a pip install with the requirements here. All the requirements are in requirements.txt. Alternatively, if you want to do conda, you can create an environment, activate it, and then do a pip install over the top of conda. But just the way things work, it's best to be doing a pip install at the end of the day. And then once you've got that, run Jupyter Lab from inside of this rllib tutorials directory. Yeah, let me see if there's... if you have any questions about installation getting set up, let us know, especially if you can ask in Q&A. That's probably the easiest. It's easy for me to pop up the Q&A. And actually, let me see if I can pop up chat. Oh, I can. Good. Great. Sorry, Zoom keeps changing everything. So, using only about 6 different video platforms, it's always entertaining to see what has changed this morning. Once you've got this repo set up and you've done installation on it, then let me jump over and do a little bit of recap. I'm going to go into the subdirectory intro RL, which is what the previous webinar was about, Introduction to Reinforcement Learning. And let me open up here. I'll take a look at Introduction to Reinforcement Learning. And for that, I'm going to shift over into my instance of Jupyter Lab. So when you bring up Jupyter Lab, it should show you on the left-hand side, there's a sidebar with a directory in it. Top level directory is the top level of the repo. And then there's a couple parts that are interesting here. One is intro RL, which was the previous webinar. The other is RL apps, which is this one. So I'm going to recap into intro RL. I'm going to take a look at the first one. And in particular, I just wanted to go back to this diagram that we had before. The idea that with reinforcement learning, you have one or more agents, like on the left-hand side, and you have some kind of environment on the right-hand side. The environment could be a simulation, as with training generally it is, or it could be some captured data that's being replayed. So there are ways to do sort of batch for training off of replay data. Or it could be an actual live environment. Say you're working in manufacturing and you've got some sort of reinforcement learning policy that's helping to guide optimization on factory floor, things like that. So the environment could be real or simulated. And then in between, what's interesting are the feedback loops. So the agent is able to observe what's going on in the environment and then takes some form of actions, and in the general case, receive some sort of rewards, as well as receiving more information about any changes that have happened in the environment. Now, we'll be talking today about some of the compare and contrast between multi-armed bandit and reinforcement learning, where some of those feedback loops are relaxed. So if we take away some of the constraints, we can come up with ways that for instance, with a multi-armed bandit, it has less of the feedback loops available and therefore can run more efficiently, if you will. So there may be performance concerns, or it may just be the use case doesn't really make sense, except for the multi-armed bandit. That's certainly the case in terms of the financial application that we'll show, balancing a portfolio, where you don't have all the feedback loops that you would expect in some other applications. For instance, any action that an agent takes in the stock market doing trades at a small scale probably aren't going to have much aggregate effect on the entire stock market. You aren't going to be able to observe the aggregate effect in the environment. So some of these feedback loops make sense in particular use cases, not so much in other use cases. And that's really the one real key thing that I want to mention here. These feedback loops are, we talk about having an exploitation versus exploration trade-off. We'll be looking at that in detail in terms of multi-armed bandits and some of the different trade-offs and consequences. The other thing is that I'll definitely recommend, as you see, there's a source here set in 2018, which, let me dig that up in a different window. Oh, come on. Great, Jupyter is not the best. All right, let me go to the second one. I want to talk a little bit, just recap about the structure of what we're working with. At a foundational layer, we have the design patterns, if you will, what Ray Core provides in terms of design patterns for distributed systems. So there's a kind of pattern language there, being able to do remote tasks, remote methods, and consequently being able to do test parallel versus being able to do actor pattern. There's other fundamental building blocks as well, like parallel iterators and job ID backends. There's a number of different components to build on. And that allows for distributed execution. Basically, you can run on a cluster or multi-cloud, some kind of mix and match of resources across multiple clusters. Up above that, we have some of the general abstraction layers, if you will, that are provided for RLlib, so that we can build out different types of reinforcement learning algorithms and environments, et cetera. So there's the RLlib abstractions is a layer above that. And then RLlib does include certain algorithms, actually quite a lot. There's also some custom algorithms that there are features so that if you want to build custom algorithms, you can leverage these abstractions down in RLlib, just as the built-in algorithms have done. And then at a layer up above that, you get more into the application layer, which is what we're working with today. And we'll be, in this case, working with, single agent represented, where environments are represented in OpenAI Gem. And I'll show how to do some customizations on Gem. Now, one caveat is that Ray includes a lot of different moving pieces. It's really, really rich in terms of what you can do with Ray, what's there. Certainly, there are some parts that are very, very mature, other parts that are more recently added, perhaps more experimental, you could say. And also, there's a lot of contributed code. So some of what we're looking at here was contributed not all that long ago by another company working in the area of leveraging multi-armed bandits. That is to say, there are parts that are more stable and others that are definitely in development. So I'll try to show through which parts are definitely more stable, what are more experimental. The other caveat is just, one thing I've found working across different systems, particularly, I do a lot of work both on Mac as well as a lot on Ubuntu, and their production environments are typically more Ubuntu. And it's not as much a problem of Ray, it's more a matter of the operating systems. But there are certainly difficulties on Mac, as you may have found. If you have a latest, greatest Mac laptop and you can blow away whatever else you have and just install the latest OS and use Brew and install CMake and build up your stack that way, that's great. If you have an Apple device that's more than a certain number of months old, then Apple will send you a polite message saying, sorry, you can't upgrade your C compiler, sorry, your C++ compiler. So you start to run into problems in terms of, all these open source libraries. Can I compile the latest and greatest? And that starts to have an impact on tools like PyTorch and TensorFlow and other things that are, dependencies for Ray. So I'm not making a critique of Ray, I'm making a critique of the entire ecosystem and some of Apple's business policies. What you may find is if you have an old Mac, compiling some of the required libraries might give you problems. You might see troubles with errors talking about PEP 517, depending on what version of Python you're using. Similarly, if you have Windows, it really depends on what's going on over in that ecosystem about C++ compilers. I'm going to be running off of Ubuntu. And really with Ubuntu, the only caveat is just discovery and management of GPU resources, depending on what types of GPUs you have and whether or not they're enabled or disabled, and whether or not the libraries can detect that correctly. That's about the only trouble that I've run into on Ubuntu lately. So if you want to have a discussion about that, it's kind of outside the scope of what we'll talk about here, but that's just a general landscape of like what you see when you're installing these packages. So having said that, I'm running in the cloud on Ubuntu, what have I got? It's some sort of 21 LTS, latest and greatest. So let me shift over into going into the bandit side. I'm going to go up to the top level and let me just check chat. I don't think anybody's done anything in chat yet. Great. Try to keep the chat window open. I'm going to go to the top level here, and then I'm going to connect into RL-apps. So there are really two applications we're going to be looking at here. The first is multi-armed bandits, and the next is about Rexus. So connect into the multi-armed bandits part. And let me pull down some of this other stuff. Clear up a little screen space. Okay. All right. So multi-armed bandits are a way to implement online machine learning, which is to say that we can leverage statistics, probability theory, et cetera, to come up with some machine learning that can learn as it's being used, is probably a good way of saying it. They're named after slot machines. So if you go to Vegas or some of the gambling center, The idea is you have a slot machine where you pull its arm, and then maybe you score triples and win a whole bunch of cash or not. So there's this idea of getting cash payouts as reward. That's where the name comes from. The idea is that with bandits, we can simulate it, and so effectively we could have multiple experiments going on at a time and pull the arm of multiple slot machines and then see what happens. There's a Q&A question. Host has enabled attendee chat. Really? Oh, goodness. Thank you, Louis. Host has disabled chat. Let's change that. And thank you, Sophia. Appreciate it. All right, awesome. Thanks, Louis. Okay, hopefully we'll get more questions soon. We'll get that fixed. Our apologies. So with a multi-arm bandit, you can effectively be doing this sort of parallel experiment of having multiple slot machines going at a time, seeing what policy gives the best rewards. And so this is a simplification of reinforcement learning in the sense that whatever action you take may not have any consequences on the environment in general. Rather, you're just trying to optimize what kind of rewards you can get out of your environment. Okay, great. Okay, great. So there are multiple types of bandits. In the base case, there's something very, very simple. We can talk about epsilon greedy. We'll look at that in a second. But there are very simplistic ones. And some of the theory for working with bandits goes back quite a long ways. You can look at the literature going back almost 90 years. So these are ideas that have been around for a while. But it does fit well into the reinforcement learning structure and architecture, if you will, of RLib, because you can implement a bandit on top of what abstractions you've already developed for reinforcement learning. Again, it's just kind of a simplification of reinforcement learning. Yeah, definitely there's this notion that Sutton 2008 is a great resource. We're going to reference that many, many times. Okay, so another concept I should really cover in terms of like the exploitation versus exploration trade-off. Certainly the idea with reinforcement learning is you want to maximize rewards. Now, we can also take a look at sort of the opposite of that, or rather a contrapositive of that, by understanding this idea of regret. So if we can understand what would have been the maximum reward in a given circumstance, and then we take a look at the actual reward we get based on our actions versus what the maximum could have been. If we take a sum of that over time, that's our regret. So, given that multi-arm bandits are somewhat simplified, it's a bit easier to do that kind of calculation because we don't have quite the state changes. Oh, I don't think we can change the chat settings now that the webinar is live. So, okay, our apologies about the chat. If you could please, let me just paraphrase what Sophia was saying. Given how Zoom is set up here now, if you have questions, please put them into Q&A and we'll cover them right away. It looks like the general chat is not available. My apologies about that. Okay, so with multi-arm bandits, we can calculate our regret. Again, it's a simplification of what we see in general reinforcement learning. There's less of a concept of changing the state as you take an individual action. So in some ways, we can start to calculate, what would be optimal in better ways. And so you see this in terms of the kinds of multi-arm bandits that are implemented here in RLib. You can see where some of this math comes in. So just to recap the terminology, we've got the state, that's the context of the environment, where the environment is now. We've got an action, that is the decision that's being taken by the agent. In other words, in terms of a bandit, which arm of the slot machine is being pulled. We've got the agent, which has the same connotations as in reinforcement learning. So there's an agent that's being driven by policy for a given environment. Reward, again, we're going to be looking at the cumulative rewards, the maximum reward over time. Regret is something that we can calculate in this case. And then exploration, exploitation trade-off, sort of balancing where do we exploit, where do we try to learn about the environment versus, where do we try to optimize the environment versus explore, where do we try to learn about the environment. And so by having that trade-off between exploit and explore, then we can continue doing the online learning and operation. All right, a question. Will the recording of this session be available to attendees? Zachary, thank you. Yes, we will have a recording of this available afterwards. Okay, so bandits are, yeah, so bandits come in a lot of practical applications. You've probably heard of A/B testing before. It's a concept that gained a lot of popularity, almost 15 years ago. Maybe even earlier, but certainly in tech companies, this started gaining a lot of popularity about 15 years ago or so. The notion of being able to do customer experiments, for what it's worth, I used to work at a company called InView, which was pretty well known for having led a lot of continuous deployment based off of customer experiments. Really interesting culture there. A/B testing is really interesting because you can do preset experiments and try a feature versus maybe a different variation of a feature and see what wins out over time. It's really an example of if you have a continuous deployment pipeline, it can be an example of online learning. It can be a great example of this sort of exploration exploitation trade-off. Because maybe you peel off 1% of your customer interactions and put those toward your customer experiments. That's the explore part, and then optimizing the outcome, NPS scores and other things like that from your customers, or other types of metrics that you're trying to optimize. That's the reward, the exploitation. So A/B testing kind of fits in with what we're describing in multi-arm bandits, and in a lot of cases, companies have shifted over to using multi-arm bandits in lieu of A/B testing, and there's some benefits there. One is that you can run multiple tests. It's not just comparing A versus B, but you can think of it almost as managing a portfolio over time. So we have certain types of feature sets that we might want to try out with customers, and maybe our customer base is changing over time. If you have operation of a website 24/7, maybe you have different customer preferences as time of day shifts across the world. You have different customer communities. So it might be that you want to run a portfolio of experiments over an extended amount of time. And the nice thing about using bandits for that sort of testing is that you can just keep them running, and just dial down effectively how much is being allocated, how much traffic goes toward the explore part, whereas in production, you're interested in exploit. So multi-arm bandits are pretty interesting for customer experiments because they give you a lot of flexibility and sort of that continuous online learning. Again, it fits really well if you have a CI/CD pipeline that you can use in conjunction with the experiments. But there's other types of applications. Certainly this fits well for, say, dynamic pricing strategies for goods and materials, services. It can work well for portfolio management, which is what we'll take a look at here. And I've seen it used in information retrieval and sort of augmented search types of use cases. Also, we can see it in anomaly detection, security applications. Yeah, this has a long history of being used in telecom. So a lot of applications, and let's jump into some of the different types of multi-arm bandit, what we can do. So types of exploitation strategies. There are some popular algorithms. Epsilon greedy is something that's very well known, and frankly, it's relatively simple. It can be a very, very short amount of code to implement this, and it can work really well, depending on your use case. So epsilon greedy, there's some approximate solutions if you look up in Wikipedia. I know they've got the greedy thing. There's a lot of variations on this, but we're not going to go into epsilon greedy because it's not quite as interesting from the coding perspective. There's another family of the explore exploit trade-off that's called upper confidence bound. And so this is something that's based more on statistics. You know, as we're going out and sampling actions and rewards, we can put a confidence bound around that. And over time, we can just go out and pick what's best based off of that analysis. So mathematically, we don't really have to learn a policy. We can calculate it statistically. And so it's interesting because this is called model-free in the sense that we don't really have to build a model. We just have to gather the statistics. So that's great. Now we can train a machine learning policy without having a model. That's interesting. Upper confidence bound is based off of, you know, what you would say frequentist statistics, frequentist notions of building a confidence interval, as you can see in the equation here. And there are definitely some trade-offs there. But you know, this can be a very powerful approach. Now, in contrast, there's another kind that we'll take a look at here called Thompson sampling. And so whereas upper confidence bound UCB is based off of frequentist statistics, Thompson sampling is based off of Bayesian approach. And so it does require a model. It can be a bit more computationally intensive. One of the problems is that, you know, you basically, the model that you're developing is your posterior, and you can have priors depending on what you know about your environment. So calculating the posteriors, of course, in Bayesian is always the potentially computationally intensive part of it. You really have to be able to model accurately about your past policy and keep that history around. Otherwise, you can start to get really large variance and have some real degradation on the policy. So there's some trade-offs in terms of what fits better, UCB or Thompson sampling. Both of these are available from a contribution not all of that long ago into RLlib. And so we have some code showing that. I want to reserve time for the applications that we have developed, so I'm not going to dig into these too much, but I will show a little bit here in a moment, a couple of notebooks. All right. So if you want to do just a real simple bandit example, we can run this here. Actually, let me clear out the outputs from prior. Okay, so here's a very simple contextual bandit. I'll import the libraries Ray and Jim. Again, Jim comes from OpenAI. It's open source for being able to represent environments that we use. And here we're going to have just a real simple contextual bandit. Okay, so we're subclassing gym.env, environment simulation. And we've got our action space, 3 discrete arms. We've got an observation space that's boxing X, Y, random variables. And then we can describe what the rewards for a context will look like. The reset is in a gym environment. Reset is where you're going to initialize back to the starting point of the simulation. And then the step is called every time you need to take an action. So the agent decides what action it's going to take and then tells the environment to take a step and then gets back its information in terms of reward or any subsequent information. So this is a really simple implementation. We'll look at more substantial work with Jim in a bit. But if we run this, so we define this class. And now we'll instantiate it. And then you see here, we say reset, and we'll take a look at what the initial observation is. Boom. Okay, so you get back X and Y, -1 and 1. And you get rewards versus what the state is. And here the rewards are going to be 10, 0, -10. And so now let's just run this randomly just to see how it operates. We'll run it for 10 iterations and just hit it with some randomly selected action out of its action space, and have that as a parameter for the step. We get back the observation and the reward, and we just print those out. And so you can see this is kind of all over the map. It's taking, at each point, it's just sampling from one of the 3 available actions and then telling us what the reward is in response. But you can calculate what the regret is, how that changes over time. Okay, and that's just running an agent at random. What we want to do is something smarter. We want to be able to learn policy, whether it has a model or it's model-free. We want to learn a policy to be able to guide that agent to take more intelligent types of actions. All right, so if we wanted to use linear upper confidence bound, linear assumes a linear dependency between the expected reward of an action and its context. And so here, what we're going to do is initialize Ray. Great. Okay. And we're going to set this up for 200 training iterations. We're going to take a look at having a episode reward mean, some sort of a cutoff there. Once we hit 10, we don't really want this to run for a long time. Just want to show what it looks like. Okay, so we've set up that stop condition as well as just a real simple configuration. And we'll also bring in Jupyter Notebook Reporter and then just run RayTune on this agent and environment. Boom. Okay, and now this is going to step through and it'll run. There's some warnings. You can ignore most of that. And as you may have guessed, we had a really low threshold for a stop condition here. Episode reward mean 10. And as you saw when we were running this at random, yeah, we could get to that pretty quickly. So here you can see really after one trial, it terminates. And okay, let's take a look at a little bit of the performance stats. Okay, so this took 3.2 seconds. And we'll take a look at what the analysis showed. Really, there's only one data point, one trial. But that's giving some idea of how we could run a multi-arm bandit and then how we could start to analyze what the results are. If you want, you can run TensorBoard, take a look at this in more detail. I'm running this in the cloud, and frankly, I was having a little bit of troubles as far as TensorBoard and getting all of the firewall rules set up. Something was not running quite as it had been previously, so I'm not going to show TensorBoard today. But if you are running on your own hardware, you can launch this from a command line, and it will leverage the logs that are produced by Ray and give you more analysis about what's going on behind the scenes, how fast is it converging toward some sort of a terminating condition. Okay, let me shut down Ray. Great. Also, I'm going to quit out of these others so that I don't have too many resources being taken up at once. Probably not a big deal, but just what I like to do. Okay, so now let's take a look at a little bit more sophisticated. If you want to set up linear UCB, you can call it from rlib contrib bandits agents lin UCB. So there's a pre-configured configuration variable. And then there's also an environment that you can use that's predefined. So, here you might want to change up some of the parameters. But again, it's kind of similar to what we saw before. We will call an instance of the environment. That gives us our agent. We'll reset it. That initializes it. We can define what it means to step through this and show a couple of explicit actions being taken, what the responses look like. But then we can go ahead and well, this would be the random case of just running that in a loop. But then we can set up ray init and run through the analysis. And so in this case, we're running it with ray tune. And that's what we did before as well. I should mention that ray tune is an optimizer. It's a way of basically structuring configuration for some types of experiments that are going to be run, and then being able to do an optimization over that. So if you're familiar with the term AutoML, this is being used a lot. Ray tune has means of doing hyperparameter optimization as one of its kinds of instances. But it also really fits well with just running multi-arm bandits. So we're using Tune as sort of the infrastructure to run these. And anyway, I'm not going to dig into too much detail. I want to save some time. But this is an example of getting linear UCB running if you want to do that. And there's some exercises at the end of each one of these each of these notebooks, by the way, if you want to dig into running these on your own, take a look at it in more detail. Shut down that thing. Shut down that thing. Yeah, shut down this one. Okay. Cool. And now, in contrast, taking a look at linear Thompson sampling, there's a well-known example that's called Wheel Bandit. And so here's an implementation of it. It's described in this paper if you want to chase the links. Deep Bayesian Bandits Showdown. But Wheel Bandit is interesting. Again, in this kind of Bayesian approach, where we can sort of manage a portfolio of experiments, how much do we allocate to each different experiment, to each different bandit? And that allocation is determined on their performance. So over time, the sort of topology of this wheel changes. We start out where, say, if we have 5 different, if we have 5 different types of experiments we can run, they start out with equivalent area, equivalent probability. But then as we start to learn about them, one of them clearly shows as being more of a winner. It starts to gain more and more of the share, and on until you can kind of see where you've got a lot of blue in the middle, and still a little bit of exploration being allocated to the things on the edge. All right. Couple questions. Michael had, if I'm not mistaken, there weren't any explicit exports of TensorFlow code. How can we still use TensorBoard for monitoring? That's a good question. Yeah, TensorBoard is great for some general purpose parts. It's not, you can use it outside of TensorFlow, is what I'm trying to say. And so inside of RLib, it can call out to TensorFlow or PyTorch, depending on the circumstances. But the thing is that as we're running Ray, it's collecting log files. And so if I get the Q&A off the side, I believe if I go back here to the top level, no, it's not going to show inside of Jupyter. I don't have my screen share set up for it, but at the top level of my user space on my Ubuntu instance that I'm running in the cloud, there's something called Ray_logs. And every time I'm running Ray, then it will capture logs of those actions, so that session, those trials, if you will. And so TensorBoard, what I was doing was pointing TensorBoard to that log file directory. And so it'll pick it up and then parse the logs and render. So you can get some better analysis about what was happening over time as you're running your trials. So TensorBoard can be really good for monitoring for that kind of analysis and visualization. I've also seen people using weights and biases in place of it. But that's a really good question. We weren't necessarily exporting anything through TensorFlow. It was just the log files. And Fatin has a question. How can I represent batch samples of a data set of network traffic as an observation space in a gym environment? Is it discrete or box space? Well, so you've got network traffic. Well, I need to understand. That's a good question. and representing the observation space can be a bit tricky in GIM. I'll show a couple of examples, a couple of very different examples of that a little bit later on. But good question, Petin. Yeah, I'd have to know a bit more about the network traffic. So, you know, there are different flavors of what kind of variables you can observe in a GIM environment. And the documentation on that is rather sparse, as I've found. Actually, some of the better advice that I have about that is if you can look at a lot of different GIM environment use cases on GitHub and study them and see how they have done their representation. That's usually a lot more effective than reading the docs. The other option is just to kind of read through the code in GIM. But a discrete variable will tell you, you know, I've got 0 through 4. So I've got 5 different possibilities and I can just index them. Whereas a box space will give you a continuous variable. So it's some sort of value, a float, if you will, that can be bounded by min and max. And so it does come down to the types of sample data that you have. You want to run a batch. What are you measuring in your network traffic? Are these things that can be represented as discrete variables or continuous variables? I'll show an example of that later because that's actually what we're going to do for the recommender system is take some samples, log files, and replay them as the environment. Good question. Okay, I'm not going to go into a whole lot of detail on the math here, but again, this is more of a Bayesian approach, whereas linear UCB, of course, you can determine things statistically without even having a model. In this case, you do need to have a model because that's representing your posterior, and the calculations feed into the posteriors. But yeah, here's just a way to show you've got Ray, RLib, contrib, bandits, agents, lints. So you've got a package there, you've got a lints trainer, and you've got tsconfig. And there's also an environment if you want to work with wheel bandit. So, you know, here, very similar thing, you'd call an instance of it, configure it. You can see here what's available on the config. And then I go to run it. Initialize Ray and use Ray tune with the environment and configuration. I'm not going to go into that in a whole lot of detail. Well, there you go. You can see how this one was trained. There's some exercises. There's also, when I ran this last time, I was catching some kind of edge case that I have to troubleshoot, and that had to do more with the system I was running on. I believe that was on a Mac. But there's some example code here if you want to try out with linear Thompson sampling. Okay. And let me go back to my directory. Great. Okay, so what I want to jump into is this example that we've put together. It's going to be under RL_apps, multi-armed bandits, and then it will be in 06 market example IPython notebook. Okay. So the idea here is, you know, sort of a simplification of investment strategy. What we did was we took data that comes from, it's published out of business school at NYU Stern, and there's basically 9 decades, over 90 years of US market data. And so if you dig it up, it's kind of interesting. Let's take a look at this table. There we go. So we've got a table that goes from 1928, just before the stock market crash, to, sorry, Zoom is in the way, to 2019. And for each year, it's recording some different signals. You've got what was the aggregate inflation rate that year, and then what was the change in terms of Standard & Poor's 500, S&P 500, which is stock market aggregate index, and shows a lot of breadth of the market. But you've also got T-bill and T-bond, so you've got short-term and long-term bonds, which of course has a lot to do more with, say, interest rates. But then you've also got Moody's. This is Moody's B, I'm correct. It's corporate bonds. So there are 4 different possible types of investment if you use this data. One is just a broad index, S&P 500 in the stock market, short-term treasury bills, long-term treasury bonds, and then corporate bonds. And so what we can do is we can think of this as a market bandit problem, where inflation that year is kind of our aggregate observation about the environment. There was some changes in the market, but then inflation went up and down. And the rewards are basically here, how much did each of these 4 kinds of investments change over the period of that year? And so this is interesting because we can replay 90 years plus of history, well, 92 years to be exact, of the US stock market, or sorry, the US investment markets in general. We can train a multi-armed bandit to be able to optimize a portfolio. And of course, this is nothing like how hedge funds and how finance on Wall Street operates these days. It's a very simplistic view of investment. Although if you have been involved in corporate HR packages and 401k programs and whatnot, it's actually not far from the truth of what individual employees have in some cases, where you only get to change the investments like once every 6 months, and you only have like 4 different kinds of funds to invest your retirement savings in. I've actually seen some big companies that do almost exactly this when it comes to portfolio management. So it's not that far afield of what individuals face. Hopefully, over time, you can move your money out to better money management strategies. But anyway, it's really good data for being able to run a multi-armed bandit. So what we've done here is put together an example, and what we'll say is, the observation is going to go in this range of inflation. In our case, we're taking a look at anywhere from 0. Well, we'll take a look at what there's actually some negative inflation in there, but there's some range of inflation, and it's bounded. And then we've got our tickers that we're looking at: S&P 500, Treasury bill, short-term, Treasury bond, long-term, and corporate. And I just have a path out here to where to access the data. So just to keep it honest, sorry, Zoom is in the way. Let me clear all the outputs and just rerun this. So we'll load up our libraries and set our defaults there, and just have a really simple function that will load that TSV file that I was showing before, market TSV. Load it up. Okay, and now let's call it. And this will give us back a data frame. So again, just exactly the same stuff, but just as a pandas data frame. We've got 92 rows, and then for each row, we've got the year, the inflation rate, and our 4 tickers. Oh yeah, and so the corporate, if you're interested, the corporate is moderate risk profile. It's the Moody's BAA corporate bonds. Okay, so if we take a look at what are the ranges going on there. So for instance, inflation, we've got 92 samples of that, and inflation is going to range anywhere from a minimum of 10.3 up to a maximum of 14.4. So we've got some range of inflation over those years. Obviously, there was a stock market crash, and certainly in my career, I've lived through a couple others. There's the famous one in 1929, but then there's also things that happened in the 70s that were, and 1950s, 1970s. Certainly, there was the downturn crash of 87 and 2008, 2009. And of course, all that's captured in this range. You can see that the returns on S&P 500, these range from basically down 40 points, up almost 60 points in terms of stock year over year. And for T-bills, it ranges from down 12 points to up 12 points. Long-term, a bit more variance, down 15 points up to 25 points. And then corporate bonds swing even a little bit more in terms of down 15, almost 40 points up. Certainly, the most change, the biggest swings are going to be in the stock market, though. All right. So let's talk about, given that we know about 90 years of data, what is the best and worst possible case? So let's calculate that. And as it turned out, the worst possible investment strategy that you could have, if you could only invest once every year, you can only change your portfolio once a year. The worst case annualized would be, you would have lost 5.64% annualized. The best case would be if you had perfect knowledge of what was going to happen in the stock market in advance, you would have been up, 15.18%. And, given what inflation rate looks like, given what typical returns look like, you figure that you're doing pretty well if you're 8% up year over year, 15% year over year, you're definitely making money. But we don't know in advance what the market's going to do. That's the beauty of it. So we're going to try to train a monthly arm bandit to give us the best return we can. All right. And so now we can visualize these. I'll just run matplotlib and do a pie plot, take a look, and you can see some boundaries there. What's the best and worst returns? You can see when the market was going through real troubles, wow, there's a really big downswing. And certainly, 1929 and subsequently, there are some problems. And you can also see some other problems out here in the 80s and 2000s. I have chat now. Oh, good. Okay. Okay, so now let's talk about developing a custom environment to be able to represent this market data and basically replay these log files that we have about the US stock market since 1928. So we'll import Gem. And now we're going to define a class, Market Bandit, which is a subclass of gem.env. To initialize it, what you saw is the defaults that I defined earlier on. We've got a max inflation rate. We've got our default tickers, the 4 different tickers. We've got the location of the data file so we can load it. But then we define our action space. In this case, there are 4 different tickers. So an action would be, where do you invest your money? And so every year you're going to choose to put it all into stocks, all into short term, all into long term, all into corporate. Again, that's kind of an abstraction, but it's an interesting thing to be able to play out over time. Okay, great. This question about data. There was a question just now about how to work with categorical data. And so that's an interesting point. Say that we had some sort of log files which were not just numbers, but some sort of strings. Could we take and pull out a dictionary of what the possible strings are and then assign numbers? So that's like in scikit-learn, there's something called label encoder that does that. In PyTorch, you've got the embeddings that do that, where we've got those kind of encodings. That would be one way. Another way to think about it would be perhaps more complex, but if you had some sort of taxonomy about what strings are available and what are the relationships between them, what do they mean, what are their neighbors, then perhaps you could do some other type of encoding based off of that, and that's where you get into more graph-based kinds of approaches. And there definitely can be some approximations off that are very powerful. So yeah, I definitely want to, there's a new book coming out. It's coming out on Manning. We just saw it got proofs on Sunday, but Dean Wampler and I just did a mini book. And one of the chapters is called Thinking Sparse and Dense. And you always have this kind of trade-off when you're working with data pipelines of having to work with categorical data and having to work with sort of more sparse sort of representations, and then eventually bring it down in some sort of dense numerical representation you can number crunch. So if you do have categorical data, if you can represent it into discrete by doing that encoding, great. If you can represent it into continuous by doing something that's more of an approximation, maybe you have taxonomy or some sort of graph to leverage. A couple different approaches there. Good question. In this case, we've got 4 discretes. So we set our action space. That's one of the fields that needs to be populated when you're subclassing EMB. And we also set our observation space. And here we've got, negative possible inflation, positive possible inflation. We just peg that at 100 plus or minus. Obviously, it only swings within a certain range, well within that limit. And then we've given a shape. It's just really one dimension, one variable that we're looking at in the observation. We're also going to keep track of a couple other things. There's the data frame where we've loaded our data so we can replay this log file over time. And that's kind of a simple hack. We're just going to load the whole thing in and replay it year by year. And then there's this variable current context. We'll use that to help provide some information back. So that's how we do the constructor to initialize a gem environment. We also need to define what a reset means. In this case, reset means, first off, we're going to set the year to the minimum, which is 1928. And then we're going to set what is that year's current inflation, because that's our observation. Set the done flag to false, and the information set it to blank. The info field here is optional. You don't really have to return any information. It's there for debugging purposes. When you're learning a policy, the algorithm does not use that field, but it is provided there by GEM for the environments to be able to help debug. And then a couple of things you need to define what a step is. In this case, step takes, well, always step will take a parameter, action. So it's the action the agent is choosing. The first thing we're going to do is take a look and say, has this trial already completed? Have we already run through all 92 years? If so, a done flag will have been set. And if you try to take any additional action after that point, it's going to come back with reward 0 and regret 0, basically a no-op. But if you're still progressing through that sequence from 1928 to 2019, then we can take a look year over year. We'll pull the data from the data frame, and we'll take a look at whatever ticker, whatever action you've selected. We'll take a look at the reward, pulling that out of the data frame. How much did the S&P return in 1953? And then we'll take a look and calculate the regret, because we can look across all those rows and find out, well, what would have been the best possible choice versus what you did. So we can calculate max reward and regret, and then we'll send back what the inflation is for that year and increment the year value and figure out if we need to set the done flag. Very simple. There's nothing here we're not going to use, but we're just including this for completeness. In case you want to use it, you can also set a seed if you wanted to be doing some debugging and a lot of trials or maybe some tests, benchmarks, things like that, and you want to set the seed for your random number generator. All right, so let's go ahead and run this. Boom. And now I've got some questions. Zachary, what's the name of the book you referenced that's coming out soon? Oh, yeah, thank you. Well, the name of the book is Hardware is Greater Than Software is Greater Than Process. And it's coming out on Manning, and it's sponsored by NVIDIA, and should be out this week. Like I said, we just got final proofs. And there's a chapter, Thinking Sparse and Dense. I'll probably be doing some talks, some webinars based on that. Thinking Sparse and Dense, of course, is a play on words from Daniel Kahneman, the Nobel Prize winning author about thinking fast and slow in terms of cognitive bias, behavioral economics. Great question. And I'll post that on LinkedIn and Twitter and web. Okay, Anonymous asks, is there a form of BPE for entity embeddings, categorical data, just like there is for, oh, yeah, that's a good question. So, okay, so there's a question here about, is there entity embeddings to work with categorical data like there is in NLP? such that when we have missing data, we don't have to just encode it as unknown. Yeah, hey, that's a great question. And that's kind of what I was alluding to when I mentioned about, wow, you could just take and look at all the possible range, like do a dictionary encoding, look at all the range of categories, labels that are showing up, and just assign a unique integer to each one. That's a simple thing to do. But if you have a little bit more information, you may know that these different categories, these different labels, have relationships amongst each other. And so you may be able to have some other representation, not just some discrete integer encoding, but instead you may have something that's probably more of like a distance measure as you move through the graph, through the taxonomy. And in that case, you know, if you had more observation data, you might be able to do some imputing, such as you know, filling in missing values by maybe training a model on all your categories and trying to clean up the data. Or you may want to collapse some of the distance between categories and cluster them. We'll show that in another example later today. So that's a really good example. So yeah, you know, sky's the limit. You can go into entity embeddings. There's a lot of interesting work done on that, because then you can look at what's being called, for instance, multi-hop problems, where you try to infer using link prediction. I know that Salesforce research is doing some really interesting work, Victoria Lin and others in that area using reinforcement learning. Nate, since the algorithms are already created in RLib, is it fair to say the hardest part about using reinforcement learning in our project is building an environment? Yes. Short answer, yes. That's certainly been my observation, is that getting the environments right was just where I spent all the time. Troubleshooting the environments, and frankly, the fact that discrete and box, you know, you can really get a lot of weird edge cases where you start to run the thing and then suddenly Jim is throwing out exceptions and you spend a lot of time trying to troubleshoot and find out why. So yeah, getting the environments right is the hard part, but also the really valuable part, because, you know, that's the use case. Yeah, I think, Nate, that's a very fair description. Although, you know, you also want to take a look and see what's happening on the reinforcement learning side. Is the math correct? If you're doing something custom, you know, are the statistics right? And also just, you know, you do want to be mindful, especially at scale, of how fast are you training? How fast are you converging on some sort of acceptable policy? How many resources does it require? You know, could there be better ways to do that? So I've definitely seen things where the algorithm on the RL side has a lot of impact. For instance, if you are using a box representation environment, one of the questions is, do you have a lot of really, really small values? And I'm not going to go off the deep end in math and talk about interval theory, but when you're working with really small values, as opposed to a big range in floats, mathematically, there are some implications. And some of the algorithms tend to kind of squish, you know, the distributions of what they're seeing on the observed variables. And so if you're working with really small values and they basically get truncated off down to zero, as some of the popular RL algorithms will do, like PPO, that can be a problem. You know, basically you end up with no information. So it's mostly a matter of the environments, but it can also be a matter of finding the right algorithms to suit. Certainly that's the case in the trade-off between like frequentist versus Bayesian for multi-arm bandits. Zach, must leave early. Oh, hey, okay, thanks, Zach. Definitely, we'll have the recording and all the codes online too on GitHub if you want to rerun it. Thank you. All right, let's get back to this. So we've defined a custom environment in Gym for our market bandit. Let's go ahead and instantiate, reset, and then just print out a whole bunch of actions. So just running this thing at random using action space sample. Okay, and you can see, here we go. We're going to run it for 10 years, and where are we? Okay, no. It was a bad 10 years in the market. We didn't do that badly, just at random. Let's take a look and see. Let's print out. Let's get a baseline. Let's go ahead and run this thing a lot, which is kind of like a Monte Carlo simulation. So if we just run this market bandit at random without any learning and takes random actions, that gives us statistically a baseline. How bad would we do? Or rather, baseline, how good do we do? And so if we look, we come back and we say 3.64%, which is sort of just slightly better than the inflation rate, although I'd have to look at what the inflation rate was during that period, because those were really bad economic years. But basically, we're tracking the inflation. I mean, we didn't lose money, and I guess if you go through the Great Depression with your market strategy and you haven't lost money, that's probably good. But we're basically tracking inflation if we just do this as a random baseline. But it gives us a data point for measuring how well is our market bandit. I'm gonna have to go faster because I know I'm running out of time. So let me just speed this up. Okay, so that's what it looks like at random. Not much information. But it's certainly better than the negative 5.64% worst case. Okay, so let's get busy here. Let's start this for real. We'll set up our configuration. And then we're going to set up our trainer. We're using a linear Thompson-Sandler trainer. Boom. And now we'll initialize Ray. And I know I'm running on 2 CPUs. I'm going to tell it that. And now I'm going to tell it, let's go through 100 iterations. That's my stop condition. And now we use RayTune with our market trainer. And we'll take out 3 samples. So, okay, this is running. Oh, goodness. Okay, good. It's running. And it's dumping out a whole bunch of information. But there you can see we've got 2 of these running. We have 2 cores allocated. There's another one pending. And you can start to see some reward information popping out. Oh, let me get to, yeah, there we go. So rewards are 600-ish over 200. We're just going to crunch through. Sorry. I'll let this thing run for a bit. But let me go ahead and run the next cell, just so we know and track. And it'll take a few minutes. I am running in the cloud. I was hoping to run on my GPU box today, but just Zoom being what it is. Okay, let's see here. Sorry, I think I saw something interesting. Good. Okay, we've done, so 2 of these have already run through. They're complete, and now we're running the last one. See, almost there, halfway through. Oh, come on. I think 80, so maybe 2 more. Okay. There we go. There we go. So both those are terminated, and it came back in about 80 seconds. Now to analyze the results, let's pull what we have back into a data frame. And so you can see the episode, yeah, right. So we run these 91 steps because we have a start at 1928 and go 91 subsequent years, but you can see the reward mins and reward means and max. And if you plot this, and this is something that actually TensorBoard does a better job. You can see it here in a data frame, but let's go ahead and plot the rewards. Okay, so we start out, yeah, they're kind of all over the map, but then they eventually converge out here. After about 5,000 to 6,000 steps, we're really starting to converge where the mean and the max are pretty tight with each other. They're tracking each other. And let's take a look at the regrets look like. Okay. And now for the big news, boom. In this case, we ran it for 80 seconds on our cloud instance. We came back with a 6.6 optimized annual return, which is actually pretty good. Okay, it's better than our baseline of like 3.6. It's not as good as the 15%. But all we have to do, I mean, the only information we have is the inflation rate that year. And the only action we can take is put all the money over into one of 4 buckets. So, you know, this is not really a super smart way of running a hedge fund per se, but that's not bad. If you could go through the Depression and those other crashes and over 90 years get 6.6% return on investment with very, very little information, that's not bad. Okay, so that's the idea of using a multi-arm bandit. And of course, we can make this a lot more complex by going in and adding more signals, not just inflation, but interest rates and other kinds of macroeconomic signals, jobless or unemployment rates, all kinds of things. We can throw that in. And if you like, there's actually some really good examples. There's the AI Economist over at Salesforce, where they've done a much more sophisticated economic simulation over time. and they can use it as a laboratory for analyzing different tax policies, things like that. But simple example. Okay, question. Louis, in the data, is it inflation from last year? Ah, that's a brilliant question. So yeah, are we biasing this with like some information ahead of time? It's a trailing signal. And yeah, that's actually something that I would like to explore and experiment with, because in the United States, the way that inflation gets reported, it's definitely a lagging signal. I mean, there has to be a lot of other agencies that report their data, and eventually it gets accumulated up and there's some official report, which is not quite the same as the market data, which, at the close of the day, you know exactly what they are. So yeah, that's one thing where I'd really have to dig in a bit more and find out, like, where was that inflation signal coming from? And was it independent analysis or was it government reporting? And if so, does that latency actually mean that we're previewing the future? And I mean, in the very worst, what you could do is just offset the inflation by 1 year and make it lag. And so you're always kind of looking back a little bit further. You would burn 1 year of your data, but that would be one way of taking more of a trailing indicator for inflation. So good criticism. I'm very curious about that. If I was doing more signals, I would be very cognizant. I'd be very concerned about, is this kind of a trailing indicator that has a lot of latency built into it or not? Fatin, what about multi-agent reinforcement learning, especially cooperative case? Yeah, that's a really good question. I mean, in this case, we have a simple multi-armed bandit. You can do one or more agents. You can get into more complex kinds of environments and more complex kinds of learning. I would definitely recommend, if you haven't seen it, there's Danny Lang is over at Unity 3D, and they have some fascinating work with multi-agents. Of course, there is also in Ray a lot of work with multi-agents and hierarchical environments and things like that. But check out some of the videos on YouTube from Danny Lang. It's really compelling, where they're doing things like curriculum learning. Really, really interesting stuff with multi-agents. As far as being able to talk about source code for that, definitely as you dig in more into Ray, there are other examples, certainly on GitHub, where people are working with more sophisticated kinds of environments. I can try to point out some of those a little bit later. Is a training fixed for the given data? Yeah, okay, is inflation evolving? That kind of gets back to, I think this question gets back to what we had asked a little bit earlier. Yeah, I don't know if the inflation is being reported the same year as the, say, the S&P and the bond data, or if there's like a 6-month lag. That's kind of questionable about the data provenance. I need to dig into where NYU got this data from and find out about how that's working. But yeah, we do have a fixed set of data that we're just running through the logs. Okay, good. Wait. Good. Okay, great questions. Let me change gears. I'm gonna drop out of this part, clear up, shut down the kernel. Hello, let me shut, good, okay. Let me go back, and I'm gonna go up to rl_apps, and I'm gonna go into Rexis. And here, well, first off, 01-Rexis is the notebook. And so we've prepared an example here of doing a recommender system. And if you want to try and run this from command line, there's also a script, rexis.py. If you want to take a look at what does this look like, not in a notebook, but actually, run as some sort of Python script. But we'll run it here in the notebook. Let me start out by clearing out the outputs. Good. Okay. So first off, the data comes from something called Jester. And it's a project that was at Berkeley. It's a joke recommendation system that they ran online for about 4 years. And so they've got 100 jokes. They collected, almost 75,000 users, 4 million continuous ratings. So it's a really interesting joke rating data set. And it's split into 3 parts. There's Jester 1, 2, and 3. We'll just take a look at Jester 1. So there's like 75,000 users. The joke ratings range from -10 to +10, and then a not rated is a 99. And you're basically looking at this log file of how people have received jokes in sequence, recommended to them, and then how did they respond to their rating. Now, the thing that's really interesting about Jester, the reason I selected it for this, is that it has a lot of what we'd say density in terms of the ratings. I mean, if you look at Movie Lens or other types of ratings data sets that are available online, they're great. There's a lot of data, but they're relatively sparse. I mean, which is to say that each user has only rated some things. And so those ratings are relatively sparse, and that has a lot of implications in terms of building a recommender system, how sparse the data is that you're going off of. In the case of Jester, that's not as much of a distortion because, frankly, it's relatively dense. A lot of people rated a lot of jokes. They got into it. There's a paper that describes this. It's called Eigentaste. So it's a collaborative filtering algorithm that Ken Goldberg and others built out of Berkeley using this data. So let's see. Let's go ahead and import the data. Boom. And do a little discovery on it. Boom. Bring it into a data frame, take a look. Okay. Now, one of the things we're going to do is go into scikit-learn and use simple imputer to be able to impute missing values, which is to say that we can look at the distribution over a column and figure out if somebody has not rated a particular joke, let's go ahead and just put in an estimator for what would have been rated, on median. And so that way we can fill in the missing values. Here we're using a mean strategy. Okay, and now a next step, let's take a look at this in terms of clustering. Like I say, we had 75,000 users. I don't want to use each individual data point. So we're going to cluster this and take a look at preferences, joke preferences, if you will, in terms of a number of clusters. But how many clusters should we have? That's the thing. Let's go ahead and, okay, we're still running clustering and on, there we go. So let's take a look. We're using k-means to cluster the joke ratings. And we can take a look, k-means, how many clusters do we use? What's our k-size? We could have done some hyperparameter optimization here to decide this, but let's just take a look at real quick visual. Certainly, you definitely pick up some performance at about k = 3 and some more performance around k = 7 or 8. It's also somewhat stochastic, depends on the randomization of when you run it. So I'm going to pick k = 7. And there's kind of a tension there. If you have too few clusters, it doesn't work that well. If you have too many clusters, you get into the density versus sparsity kind of issue. So 7 is kind of a mid-range where the decrease in error is starting to level out our clusters. But it also gives us a number of clusters to work with. So too few clusters equals poor predictions because of precision. Too many clusters, less recall. So we'll peg this at 7. And boom. And then what we're going to do is use scikit-learn to go in and cluster the data and then label it based on the cluster centers. Boom. And we'll use that for our training data for our recommender system. Let's just plot this out. It's kind of a monster, but you can plot all these different clusters on here. And you can see that, there's some that definitely spread over. The yellows get really clustered up here. The greens are kind of way, way out. The blues tend to be over here. So, I mean, this is a two-dimensional representation of a 7-dimensional problem. But you can see that clustering has some benefit. Now, what we're doing is to build a recommender system using reinforcement learning, having this joke data that's already been clustered. And in a classic collaborative filter, going back to Sasha Cheslenko and Patty Mize and others back in the mid-90s, the original collaborative filtering online with systems like Firefly back in 1994. Yeah, it's very similar to what Amazon implemented early on. People who bought X books also bought Y books. And that's great. That really scales. Doing that kind of item-to-item collaborative filter scales really well. But on the other hand, it's a little bit of a distortion because people change preferences over time. I used to work in advertising, building recommender systems or leading a team building recommender systems. And the joke was that like the most expensive advertising was buying pre-qualified leads for people who wanted to buy a Mercedes-Benz automobile. And the joke was that, these ads had a really high price tag because they're really valuable. But, the moment that somebody buys their Mercedes, that's the last ad that they're ever going to click. So the joke was these are really expensive ads to buy. The moment somebody buys the ads, they're completely worthless. And you don't know. So, the thing is that people's preferences change and it creates a real distortion if you're doing a simple item-based collaborative filter. And if you're in advertising, you find that out very quickly. There's a great article about this from Julian Macaulay about the evolution of beer preferences. Because as a graduate student coming to the US, finding out about beer preferences in the US was quite startling to Julian. And so he wrote some papers about it. What we're going to do is use reinforcement learning to build an item-based recommender system that can evolve over time. So getting back to this notion of online learning, getting back to this notion of the explore-exploit loop. Okay, let me, Zoom is really causing me problems. I know I'm almost running out of time, so let me go quickly. What we're going to do is represent that we know from the data there are some jokes that have a lot more density than others. And so we can use those as a way of kind of bootstrap, as a kind of warm start on the recommender system. Almost everybody has rated these jokes. So what we can do is when we have a new user coming in the system, we can just throw out one of these kind of jokes, sample from that, take a few of those and start to get a feel for what clusters are they near. And then over the course of time, as a reinforcement learning algorithm kicks in, as the agent is learning about its environment, we can start to figure out how does a person fit into one cluster or another, or rather, how do they jump from one cluster to another? And we'll use the clusters then as our basis for recommending what jokes to give them next. Okay, so get that. Okay, so we're going to go in and build a custom gym environment. And here we've got joke rec, it's subclassing gym environment. We've got our cluster centers or labels, and our observation space is based off those clusters. Our action space is basically which cluster you're choosing. And so we want the agent to say, sample a joke from cluster X at a given point in time. And we want that to be able to fit with what the preferences of that individual user would be. And then we'll compare that with the log files, what the ratings were, to tell us what the reward should be. Now, one other thing that we're going to add in this gym environment is a method called render. It's optional, but it allows you to do some debugging, rendering how things are going. Okay, so we've got this defined. Our next step is let's bring in Ray. And so next, we will instantiate jokerec with our configuration and we'll reset it. So we're initializing it. Let's show what happens when we just choose an action at random and further apply an action at random and see what kind of observation we get back. Okay, there we get how far away are we from the different cluster centers, and also what is the reward for choosing that last joke. But we can also render this, which gives us a little bit better information. It's the same data as what we have up here in observation and reward, but a little bit more information. Pretty much the same info. Okay, great. So now what I'm going to do is run through one episode. I'm going to take that through max steps and just run it, and we can calculate a baseline. So we're going to iterate through and boom. Okay, so we're going to run this baseline 1,000 iterations, and what it comes back and says, well, a random baseline there, you would have gotten an overall rating for this user of, or for a hypothetical user of -0.4. And so this can tell us how well we're learning with reinforcement learning, or how far are we above that baseline. Okay, so first off, I'm going to clear out the log files that I had from previous work with multi-arm bandit. I'm just going to do some shutil to clear out the junk. Now I'm going to initialize Ray. Boom. And then I come in here. I'm going to call RayTune registry. There's a method in there called register env. So I've got my environment from Jim. We'll call that joke rack version 0, and we'll register it, and then we'll use proximal policy optimization, PPO. We'll create an agent that way. Okay, great. And now I'm going to come in here and run 20 iterations, 20 epochs. During each one, I'm going to capture what is my min, mean, and max reward, what was the length of the episode. And so this is basically where we're training the policy. Take this. This is going to run a little bit. Come on. There we go. Now it's kicking in. And you can see first time around, got a reward -26, but the max is 45. That actually did pretty well. Next time around, the max is still the same, 45.22. The reward is actually dropping, but you see the mean reward has jumped up. So the reinforcement learning algorithm has already figured out how to get a good maximum reward, and now it's trying to bring up the mean reward. And meanwhile, the min reward is still bouncing around all over the place. At each point in time, you can see that there's a checkpoint being saved. So we'll take the policy at that state and save it, and then we can reuse it later as a starting point, for instance. You can think of that as sort of like a model deployment. That's the reinforcement learning of the version of a model deployment. Right now we're into 5.6, and you can see the max is actually increasing now. The mean a little bit less, but now we've stabilized on the min reward. Now the min reward is starting to come up a bit. We'll have 3 more of these and we'll be done. Boom. Okay. Good. And so, I mean, when you think back, the baseline, the random baseline with 1,000 trials, we came out with -3, and already our mean is, well, there we go, positive 3.7. So we're already operating above baseline. And I think we're done. Yeah, okay, and so the last one there, we got 7 as a rating. So we're well above baseline. Let's take a look at this. Let's simulate a use case of running this in production. Again, with reinforcement learning, we call this a rollout, where we take a policy and then run it through. It could be a simulation, or it could be swap out the simulation with the live environment. We'll define how to run rollout, and now let's run this over 500 iterations and print out. Boom, boom, boom. What are we doing? Huh. And I'm not quite sure why that's not responding. Interesting. Oh, well, any questions up to this point? This is probably, while that's crunching along, it's probably a good point to jump into any questions you might have. Good, Q&A. So if new jokes come in, can you still use your old rollout with the, yeah, exactly. You roll out the clusters and users might see the new jokes. Great question. So what we've done is to take our whole space of possible jokes we could select and cluster them. We put them into 7 clusters. If there are new jokes that come in, how do we handle those? So one of the really easy ways would be to say, which cluster is this joke closest to? And if so, then add it to that cluster set, which means that now we have a larger set to sample from. Now, over time, you probably want to rebalance that. You probably rerun your clustering. Maybe that's some sort of nightly or hourly batch. But you could see where you could get more of a continuous process for deploying new jokes, but also bringing in new people. Great question. Sebastian, shouldn't you set the Explorer to false when you're rolling out? What kind of agent did I use? That's a good question. Let me take a look. Action state false. Well, I mean, I have a verbose flag. Sorry. Yeah, I'm gonna have to switch out of this window and find out what's going on. We are coming up on time. For whatever reason, my rollout is, oh, right, sorry. Mea culpa, I really blew that. We're still training. So I had set it to 20 iterations. I thought we only had 10. So yeah, we're up to iteration 20 now. And as you can see, the max rewards, we got a pretty good mean reward, and now we're building up on the min reward. Right, so we're still training. But we're 2 away from that. Almost done. Yeah, so rollout hadn't even had a chance to execute yet. And one more. Oh, okay, so the min reward is -19. That's actually in -18. We're seeing some pretty good numbers there for the min. And there is checkpoint 20. Okay, good, that's completed. Okay, and so we define the rollout, great. And so now here we start to use the rollout and run this 500 times. And you can see you're getting different cumulative rewards. So effectively, this is looking at different users, trying out the policy on them. So you're gonna get a range of different rewards. Not everybody likes the jokes. But the recommender should be scored, you know, in a few different ways. I mean, you wanna look at kind of in aggregate across your entire population base, how good are your recommendations being considered? But then you also want to look at, you know, like what's the worst case? Anyway, here's 500 of these all brought out. And let's take a look. That's still crunching along. Doing a rollout. Yeah, okay, good. I'm getting some good rewards. Better rewards than the bad rewards. I wish I had a way to, I should have some sort of dynamic update on the visualization. Now, the next part that I was going to show was just what the train policy looks like. That's where I do a base model summary. And it's some information. It basically tells you what that neural network looks like, the different layers. It's more just a matter of topology. It's not going to give you much information. The real information would be running TensorBoard. And so again, tilde/ray results is where my log files are. If I were to run that, I had some problems with firewall earlier on, but I can show it. But yeah, that's where we're at. That's our recommender system. And I know we're a few minutes over. So let me open it up if there's any questions. So Anonymous asks, all the environments shown, we have the data already. We're making an environment with the data. How can we do this with some real world mapping to an environment which is dynamic? That is say, okay, so how can we include, oh, okay, great. Sure, that's a great question. So in this case, we had some canned static data sets and we were rerunning them as a simulation. And the thing is, with reinforcement learning, yeah, you want to run lots of simulations so that you can build up your machine learning to come up with a good policy. The question is, though, what if you want to use live data? So let's go back and take a look. So if I scroll back up here to where we define the environment, one of my configuration parameters was essentially saying, where's the data set? Right there. And so I'd given it a file path of where to load that data. So imagine if instead I could have had a pub sub and some sort of stream that I connect to and just consume off that stream. then I can have a real-time online learning recommender system. And so I recognize some names of the people who were in the chat earlier this morning. And certainly if you roll the clock back to 2014, when we did the real-time language identification on Twitter examples with Spark streaming, that some of you I know were actually in those demos. The idea is you can hook up a stream, and then you could be doing some type of dynamic clustering if you're using that algorithm. Of course, I was using something very simple. I was using k-means, but I could have more of a dynamic streaming, or I could take many batches. I could take windows of the stream, rerun the clustering, and then reevaluate my clusters. That would be a way of handling live data. But it also just depends on live data in terms of, can I use some historic clustering, but I have live data from actual users, so I'm presenting them with a joke, and then the reward and regret is being calculated based off of that observation, is based off of their live answers. That would be the other side of having live versus canned data. So that gets into more of a deployment, but certainly you can rework Gem. I could see hooking this up to some sort of streaming client off of Kafka, Pulsar, Spark Streaming, things like that, or any sort of message queue, PubSub, etc. Any other questions? Let me see. I don't know if I can't change over into chat. We're about 10 minutes over, but I'll stick around here for a while if anybody has questions. I do want to wrap up the recording. I think that once I stop, I may end the recording. If you want to get a hold of me, I am Pacoid on Twitter. A couple of things I did want to show. Let's see. Let me jump around here. Sorry, I've got Zoom in the way, so it's hard to see what's going on. One of the things I can show is wow. There we go. So if I go up to my top level directory, I've got this directory here, array results. If I go into there, you'll see that I cleared out everything before I ran jokerec, and so now I've got PPO jokerec version 0. Push into that PPO, and if you want to go through the directories there, basically this will be keeping track of all the results. CD that. And so this is the data that that TensorBoard would be running against. Another thing I really want to show is here, there's a repo called gem_example. It's under Derwent AI. And so this is the basis that we're using for a customized gem. There's a lot of different use cases for OpenAI Gem. I want to try to build something that integrates well with Ray RLlib. There's a few caveats there. So if you take a look at the code, you can use this as a basis. You can just import this, pip install or whatever, but this will show you how to set up an example gem that you might want to use with other projects. So I definitely want to include that as an example. And the last thing is that I want to put in a plug for, Ray. Sorry, Zoom's getting in the way. Ray Summit. We're going to have Ray Summit coming up in, there we go. Ray Summit is coming up next month. It'll be on June 22nd is when we have our tutorials. I'll be teaching Ray Core in the morning, and my good friend and colleague Sven Mika will be teaching RLlib and going into a lot more advanced patterns of the RLlib. So there's a half-day course about reinforcement learning on June 22nd at Ray Summit. You can sign up for the conference. It's for free. You do have to register in advance. Definitely want to check that out. The other thing I definitely want to point out is if you have questions, let me go to the ray.io. There's a really good forum. If you go to ray.io.forum, there's a discussion board. This is going to be one of the best resources for getting in front of other developers who are working in reinforcement learning. You know, a lot of what I've shown today is just really simple examples because of showing them in a tutorial. If you want to get into more sophisticated examples, obviously, where you're using different types of algorithms, the RLlib part of the Ray discussion board is a really great resource for that. As I mentioned, Sven Mika is teaching. Sven will be teaching the RLlib course at Ray Summit, and he's a really great person to get in contact with on the discourse board if you have any questions about how to use this API. No open questions there? All right. Alrighty, so if there's no other questions, please feel free to link up with me on LinkedIn and Twitter, and thank you very much.